For the shapes homework, I've pulled some questions that I think are indicative of what you can find on the quiz. Now, some of these questions are more comprehensive than what you'll find on the quiz, and what you'll find on the quiz are actually these questions in parts. So we'll start with number 1. So for this molecule, this is chlorine pentafluoride, we're supposed to draw a Lewis structure and answer these questions. So you will be uploading something to the file upload for this quiz. So for chlorine pentafluoride, we're going to start with our chemical formula. And then we're going to count our valence electrons. Chlorine brings 7. Each of these fluorines also brings 7 for a total of 42 valence electrons. So that number needs to go there. We're going to draw this Lewis structure. So I'm going to start with my central atom, and then I'm going to draw my terminal atoms along with it. Now I'm going to distribute my electrons. So here I've used 10, and I'm going to distribute the electrons in order to satiate the octet rule for these fluorines. Now when I do that, I have 8 times 5 is 40. I've used 40 electrons, so this other pair must be on chlorine. So this is the Lewis structure. Now we need to calculate the formal charge on chlorine. To calculate the formal charge, we start with the valence electrons. Chlorine comes in with 7 valence electrons. We're going to subtract the number of bonds around that atom. Then we subtract the number of non-bonded electrons, not pairs, the actual number of electrons. So the formal charge on chlorine is 0, and that needs to be entered here in the box. We also need the electron geometry and the molecular geometry. Here we have 5 atoms and a lone pair, so the electron geometry has 6 terminal things, and then 2 and up and a down. So there's 1, 2, 3, 4, 5, 6. So the electron geometry here, this is going to be octahedral. But the molecular geometry is going to be different because one of these is an electron and the other one is going to be an atom. So because of that, we form this square pyramid. Now the system will take either square pyramid or square pyramidal. They're equivalent. Remember, I will look over everyone's assignment individually. You can use this space in order to upload a file to support your homework. Number 3. The nitrate anion, we're going to be drawing all resonance forms and indicate the formal charges. Now I would suggest that you do this on one page. You can actually upload the one image to this question if you don't want to also upload a separate file for number 1. That's fine. So the nitrate anion is NO3 minus. We need to count all of our valence electrons. Nitrogen comes in with 5, each of the oxygens comes in with 6, and then we have 1 electron for our charge. So we have a total then of 24 electrons for this anion. To draw all of the resonance structures, we start with our central atom and then bond our terminal atoms. And I'm just going to start with the double bond over here on the left, and then that double bond rotates. The double bond in, but you do need to show all 3 of the resonance structures. Now to calculate the formal charge, I'm going to assign this oxygen is 1, this one is 2, and 3, and I'm just going to do that along the top here in order to identify my oxygens. So then I'm going to create this table, O1, O2, O3, and then I'm going to fill in the data. So I have the number of valence electrons minus the number of bonds minus non-bonded, and that's going to give me my formal charge. So I'm going to create this table, V, B, NB, FC, and I'm going to create it for each of these structures. So here I've filled in the table. All of the valence electrons will be static because each of the atoms comes in with the number of electrons they come in with. And then the number of bonds will change. Now for nitrogen, the number of bonds doesn't change because we're actually rotating that pi bond around the nitrogen. So the formal charge on nitrogen for the nitrate anion is going to be +1, regardless of the resonance structure. And then the charges on the oxygens do shift. So you can see over here in this first resonance structure that I have here, the formal charge on this oxygen is 0, but each of these oxygens is a -1. And it rolls around that way so that the oxygen that has the double bond has the formal charge of 0. So this is what I would expect to see for the formal charge part. Now let's make sure that what's the hybridization on each atom. So when you have a pi bond, the hybridization, what happens is all of these atoms are coming in with an S and 3 Ps. And when you have a double bond, that's a p orbital overlap. So this S, this nitrogen, the p is occupied by that pi bond. That's what this is. This is a p orbital overlap. So sp2 is all that's left in order to create that pi bond, but these are sp3 hybridized orbitals. So that's how that works. This is sp3, the one with the double bond is sp2, and then the other oxygens are going to be sp3. So that will answer that question thoroughly. Number 4, we're going to go off molecular polarity and determined by Vesper theory, and we're going to look at a couple of compounds and determine whether they will be soluble in carbon tetrachloride or in water. So in order to do that, we need to draw our Lewis structures. So the compounds I'm going to have you look at include carbon dioxide, ammonia, xenon tetrafluoride, and boron trichloride. So the first thing we need to do is draw all of these Lewis structures. Now carbon dioxide is one that's quintessentially used in order to show a linear relationship. Ammonia is usually used to show the trigonal pyramid. Xenon tetrafluoride has 4 of these, and then it also has 2 additional lone pairs on the xenon, and they orient away from one another. So although this is a square molecular shape, it is an octahedral electron geometry. There we are. Now the boron trichloride. Boron is one of those atoms that doesn't want an octet. It's one of our exceptions. So this is a trigonal planar structure. Now we draw the polarity of our bonds like this, and because this is trigonal planar, this is a non-polar molecule, so we would expect this to be soluble in carbon tetrachloride. Xenon tetrafluoride, also non-polar, although there are polar bonds here. With the fluorine pulling those electrons away from the xenon, they're pulling equal and opposite. And then the lone pairs pull equal and opposite as well. So we have nonpolar. So we would expect this to be soluble in carbon tetrachloride, not in water. Ammonia, on the other hand, this is a polar molecule. All 3 of these polar bonds point up towards the nitrogen, up towards this cloud of electrons here. So this is a polar molecule. And because it is polar, we would expect it to be soluble in water. Carbon dioxide pulls equal and opposite. This is a canceling shape. It is linear. This is a non-polar molecule, so we would expect it to be soluble in carbon tetrachloride as well. And that should answer number 4 fairly thoroughly. Now you should also be able to define or explain differences between sigma and pi bonds, as well as covalent and ionic bonds. I will also need you to be able to relate electronegativity differences to bond polarity. Explain to me in words how the electronegativity difference lends to the polarity of a bond.